All right, we're going to take a look for this day 2 at some exponential functions. So we're going to start talking a little bit about the applications of exponentials and what this means in a real life situation. So we're going to look at the kind of the standard format for these equations and how they relate to the ones that we were graphing yesterday. So basically our regular y equals ab to the x just gets a little bit more involved. It gives us a little bit more information when we look at the standard form of this. So our y value is still always going to be this final amount, the value of the function at a particular time. In the equations that we did yesterday, A represented that stretching and compressing. When you think back to the graphs that we did yesterday, the parent graphs, all those parent graphs have a y-intercept of 1 because when you take anything to the 0 power, it's a 1. So if this value here is a 1, when you multiply by A, you're just going to get 1 times a, which will be a. So the initial or starting amount then is always this value out front, this y0. It's whatever it is at time 0, so like that y-intercept value. So that initial starting point in your population, whatever it is you're looking at, either growing or decaying. Now your base, let's talk about bases that we did yesterday. If your base is greater than 1, that's where we have growth. If the base is between 0 and 1, that's where we have decay. So when you think about our base in here, that's where that adding and subtracting comes from. If you're adding your rate, that would give you a base that's bigger than 1. You'd have growth. If you're subtracting the rate, that's when you're going to have a decay situation. You're taking it away, it's going to be a number less than 1. So that's the interest rate per time period, whatever that time period might be. Then the last thing, when we take a look at the variable here, is the t. So when you think about exponential, it means the variable that determines our value, the change, is happening in the exponent. That's what exponential means. So the variable that's determining our amount is this t, this time period. So how long are we looking at this change occurring? So the longer something is growing or decaying, that's going to determine our final value. So we're going to look at some just kind of general growth and decay models, and then we're going to look at some applications that have to do with financial things, which are very applicable to everyone in the future here. Okay, so one thing we're going to take a look at is research. So in research, we talk a lot about things that grow or decay, or they look at populations, and this is one example. There's been a lot of issues with honeybees and the honey market, and just the population of bees has been decaying, and it's for a lot of different reasons, and it's causing a lot of trouble because bees are a really important kind of part of the infrastructure. So what's happening is there's these little tiny bugs that are causing problems with the bee population. It's actually affecting how many bees there are. So they had some research going on. They did some of this even at the University of Minnesota. I know I saw a special on that not too long ago about how this little mite, this invasive species, is coming in and causing trouble. So they were calculating and counting how many were present and calculating the rate of growth. So we're going to use this as our example then, that they have this colony of these little mites that's growing at a rate of 14% per week, and their initial population that they counted, that they surveyed, was 500. What's the expected population down the road, like in 22 weeks? So why would they care about this? Well, if the population is growing very quickly, it's affecting that bee population. So if you want to make some sort of change or intervention, let's say, you need to know what the time frame is, what kinds of things do they need to do to prevent that. And this could be any kind of population growth. It could be of a serious disease, a virus, something like that, where they want to project so they can help make decisions and try to affect some change. So being able to model how something is growing or decaying is a really valuable thing to be able to deal with. So in our regular, just kind of general growth and decay, let's talk about what we're trying to deal with. What is the expected population? That's the y. That's what I'm trying to figure out. The y0 is my starting population, that initial value, 500. The rate. Let's talk about why I picked plus. Well, this is growing, it's increasing, so I have to be adding to that rate. If my rate was just a 1, if I didn't have this at all, and my base was just a 1, what would happen to my population? Well, nothing. It would stay constant. If I multiply by 1, it'd be 100% of what it always was. But I'm adding something to it because it's growing. So my interest rate being 14% per week, I would say 0.14. Okay, now let's talk about time. T in general would be in whatever this is per unit. So it's in weeks. They're asking me to figure out what that time or what that population would be after 22 of those weeks. Be careful that these two are representing the same thing. I could have said, what's the population in 156 days? And you'd have to do that conversion. So make sure your rate of growth is the same unit as what your time is that you're trying to figure out. All right, so let's go ahead and model this with an equation first. So my initial population is 500. and it would be 1 plus 0.14. And initially, I'm just going to say to the t. I want to talk about what this equation would represent. So 500 times 1.14 to the t. This equation, if you graphed it, so if you took a look at the graph, it would have that starting value there at 500, and it would be growing. That equation represents then all of the population values over time of this colony. So at any point in the future, I could take a look at whatever week it was, and I could tell you that population. So it would be representing that, that final amount over any time in the future. That's the real power of being able to write and model an equation like this. So it's in general, over time, what would that population be? So it's growing at a rate of, look at your base. What does 1.14 mean? 14% growth. It's 114% of what it was prior. So it's telling me exactly what's happening in that population. So I'm starting with 500, growing at a rate of 14%. So now what would it be after 22 weeks? Raise it to the 22nd power. Do that calculation, you come up with 2,838 and point, oops, sorry, that was the wrong number. Multiplying the wrong thing. It's 8930.5. Double check all of these on your calculator. Make sure if you need to pause the video and calculate, it's really important that you try it yourself. So for this one, you could talk about, does it make sense to round? Do you want half of a mite, like half of a cute little bug? Or do you want the whole thing, depending on what you're going to do with it? But we can model. That's a huge growth. Almost 9,000 already, 22 later, starting at 500. So what kinds of decisions need to be made then to help with that situation? So being able to model when you multiply by something, so it's not constant growth, it's not linear growth. This is multiplying. It's a percent increase, a percent change, not just a constant rate of change. This is an example that you guys used last year as well, compound interest. So anybody that has a savings account deals with compound interest. So the bank will give you a percentage of your principal, the amount that you have in there, for keeping your money with them. So it's a good situation, better than your piggy bank at home. We have this still A, B to the X kind of scenario though. Your final amount is your account balance, that's like your Y. Your initial amount is your principal, that A value out front, that initial amount that you put in the bank. So say you open your savings account with $100, that P would be 100. All right, now the base, this whole thing here is the base. So that's going to be bigger than 1 because remember we're adding, and I hope it is, because if your bank is taking money away from you for putting money in there, you need to change banks. This is not where you want your money. We want to be adding that. So it's R over N. What does that R over N stand for? R is the amount of interest per year, the annual interest rate. So how much you'd earn in the whole year. N is the number of times that they give you interest. How many times a year do they pay it out? They call that compounding. So that's why it's called compound interest. So how many times is it compounded per year? Compounded means calculated. How many times do they give it to you? So they take that entire interest rate over the whole year and they divide it up per payment. So say you earn 12% interest and they're going to give you monthly interest. Well, that means they're going to take that entire 12% and they're going to divide it up over 12 payments. So what you're really going to get is 1% for each payment then. So by the end of the year, you will have earned a total of 12% altogether. So they're giving you that part per payment. And then the exponent. Let's talk about the exponent for a second. The exponent, remember, is what varies, what changes. That's why we call it exponential. Is n times t. What would that represent? N is the number of times per year you get interest, and t is the number of years that you're looking at total. So n times t would represent the total number of payments of interest that you will get. So the total number of times that your interest is accrued or compounded over the course of the time you have the money in the bank. So it's going to give us that total number of times. So I want to try a couple different scenarios with this just so you can understand really why the numbers are doing what they do. So determine the amount of money that you would have in an account that earns 5% interest compounded daily if you invest $2,000 and it's left in the account for 7 years. All right, so let's talk about why this is an exponential. So first of all, what's changing, what's going to determine how much money we have is the time that we leave it in there. The longer we leave the money in the bank, the more interest that we're going to earn. So we have an initial investment of $2,000 that we're putting in the bank. The interest rate that we're earning is 5%. and we're compounding daily. So this is great. The more number of times per year you compound, the better it is for you, because then you take that interest, it gets added into your account, and you have more money. So the more frequently they compound, the better scenario it is for you. So to the n times t, so that's the total number of times you're getting interest paid per year, 365, times how many years you have that in the account, which is 7 years. So let's see what that nets out to be then. So 1 point, whatever that is. I just want to get this number in the exponent here. So 365 times 7. So how many total payments is 365 times 7? So I want to calculate that so we can see what we're dealing with here. So we have 2,555 payments or times that this interest is going to be accrued. So that's what that power means. When we multiply by this growth rate, 2,555 times, then we're going to be getting interest that many times over the course of that loan, which is a lot. All right, so this comes out to be $2,838.07. Try it on your calculator, make sure you're good. All right, so what does that mean? How much do we actually earn in interest then? Well, you put in $2,000 yourself, so the interest that we earn then would be the difference, which is $838.07. So not a bad deal, but this is definitely not the kind of situation where you'd want to be saving for retirement in an account like this, or saving for college, because that would only buy you a couple, probably 2 or 3 books at college. So we want to have a little bit bigger sort of investment scenario for that. But it's a great way to be able to see how interest can work for you. So that base is the growth. It's telling you what percentage you're getting per payment, and then how many payments are you going to be made. That's your exponent. That's why it's changed over time, and it's exponential, because you're multiplying by that base. All right, let's try one more of those account scenarios. This is pretty common. Some people try to think about, what would I have to put away now to be able to save for the future? So this is a situation where you want to put money in the account now. So I don't know what that principle is, to be able to have $25,000 down the road for a purchase, say. So this would be a great situation where if it's about 10 years, say you're going to be figuring you need to buy a new car in about 10 years. And for a lot of you, that might be the situation you'd be in. Once you graduate from college, you need a vehicle. So what would you have to be able to put away now to have $25,000 saved up in 10 years to be able to purchase this car? So it's earning 6%. And let's talk about this. APR, that's short for annual percentage rate. So that's the rate of interest for the entire year. So they're going to give you 6% over the course of the whole year, but they're going to give it to you quarterly, and quarterly would be how many times? That would be 4 times per year. So the R divided by N is the interest per time they compound it. To the NT, so we're going to do this 4 times a year for 10 years. So let's think about what that means then. When you divide 0.06 divided by 4, you get this to the 40th. All right, now I want you to think about what those numbers are telling you. So let's look at the base. What does that mean in terms of growth? What percent growth would 1.015 be? Well, that would be 1.5% growth. So that means that 6% is divided up equally over the 4 times per year that they're going to give it to us, which means we would get 1.5% interest each time they compound. So when you look at the base, that's what that's telling you. They're multiplying by 1.015. 1 is the amount of money you had already, plus the 0.015 that they're giving you, that 1.5%. All right, now what does the 40 represent? Well, that's how many total times you're going to get that interest, right? Because you're going to get it 4 times a year, times the 10 years that you have your money in there. Okay, so order of operations, then you're going to figure out what this number is and take 25,000 divided by that payment, or by that value, and then we'll see what our P is. So I ended up with 13,781.56. See if that's what you're coming up with as well. So when you think about that, that's a lot of money, man. You're not gonna have we're gonna have to have quite a bit saved up already if you want to have 25,000 10 years down the line. So you're pretty much doubling your money, I guess, pretty close to it. But you do have to have a lot already in order to have that. So if you're trying to do a long-term investment, this may not be the best way to go. You may want to invest in something that has a little bit higher return. Which brings us to something that you probably haven't talked about. We're going to talk about something called an annuity, where you're making a series of payments at regular intervals. What we were just talking about is you plop the money in the bank and you just let it sit there. didn't do anything else. You didn't keep putting money in. You just let one amount of money sit. An annuity is where you make regular payments, regular intervals. So like every month or every week, you're either putting money away to invest, or you're paying something off, like you've borrowed money. So we're going to talk about both scenarios. So the first one is called present value. That's where you are borrowing. So when you think of present value, think of it as a borrow situation. So you want to have the money now. In today's dollars, I need the money. So like a mortgage, a college loan, so things like that. So if you're borrowing for college, so you say you need to borrow $100,000 for college and you need it now to pay your tuition, then you're going to have to pay it back in these regular payments. That's what we're talking about. So the PN is the present value. That's how much you're borrowing. The P is your payment, like how much per month or whatever you're going to be doing. And let's talk about the other two. They tried to make it fewer variables. So the I in this formula is the same thing as the R over N was in the last one. It's the interest rate divided by the number of payments per year. It's the interest rate per payment. So the APR divided by the number of payments per year. It's just like the R over N. And then the N, just to make things a little bit more confusing, the N is the total number of payments that you would make in this loan for the entire thing. So it's like the NT. So the exponent is the same and the I is the same as what we were doing in those same positions in the last formula. So it's the interest rate per payment still, and it's the total number of payments. So we're going to go through and do a calculation for purchasing a home. The same thing would happen if we did it for a college loan, same sort of idea. So I want you to get a real idea of what these numbers are looking like. So what would the monthly payment be on a 30-year mortgage of $250,000 at 6.5% APR? Now, people do a lot of different things to try to find a home that's affordable, and it's the same thing for college loans. The things that can affect how much you pay. Think about what you have choice over. Certainly the amount of the loan. How much are you borrowing? What's my interest rate? The bigger that is, the more I'm going to have to pay back. The length of the loan. The longer you spread it out, the smaller your payments are going to be, but then you're going to be paying more in interest. So there's a lot of things that can vary to have an outcome on how much things are going to cost for you. So it's a very important conversation to think about. But when we do our calculation here for our present value, what we are trying to solve for is that payment. What is it going to be per month? So I'm just going to have the formula written here so we can kind of all be looking at the same thing at the same time. Let's go through and see what we know. We know we're going to be borrowing $250,000, which is pretty close to the median home value in Hastings. We're looking for our payment. 1 plus, let's talk about I now. So I is the interest rate per payment. So we're paying 6.5% interest and we're making monthly payments. So they're going to take that 6.5% and spread it out over 12 payments each year. To the negative N. N is the total number of payments that you're going to make. So over a 30-year loan, paying 12 times a year, you're going to be making 360 payments. So make sure you realize that's a negative exponent. So that's a 1 over, that's a reciprocal. And then divided by I again, which is 0.065 divided by 12. Okay, so this is one of these scenarios where it's really important to kind of think big picture and type it in correctly. You need to figure out what this entire number is in the brackets. We need to know what this number is, and then we're going to take 250,000 divided by that number to be able to see what our payment is. So I'm going to go ahead and kind of walk you through order of operations, what I would do to find that calculation. So I would start inside the parentheses here. So I'm going to do the 1 plus 0.065 divided by 12, and then raise that to the negative 360, and then do 1 minus that answer. So don't round, make sure you get all the digits. So either copy or use your answer function. And then divided by oops, I almost did what I didn't want you to do. So make sure you use parentheses there. You're dividing by the whole denominator, so 0.065 divided by 12. So use parentheses down there. You should come up with this. Now, just for writing it down purposes, I'm going to round. But don't round when you do your actual calculation. You want to make sure you have all of the digits. So use the complete number then when you do that division. So 250,000, make sure I get enough zeros here, divided by my answer would give me a payment of $1,580.17. And they will round to the nearest penny when they talk about those payments. So when you go online to make your payment, you'll be making a payment of $1,580.17. per month. So think about income that you already have right now, your part-time jobs and everything. That is a lot of money per month to be able to do something like this. All right, so what does this really mean? So here's where we get into the real nitty-gritty. What did your home actually cost you? You made 360 payments, remember, over the course of this loan of $1,580.17. So that means your actual cost of your home would be that product. And again, use the rounded number this time though, because your payment would actually be 17 cents. That's $568,861.20. It's over $500,000 is the actual cost of your home. Remember, you only borrowed $250,000 from the bank, right? And you end up paying back, if you take 30 years to pay this off, $586,000 and some. So what does that mean for you in interest? This is a very sobering thought here, but that means in interest then, we would find 568,861.20, subtract off that 250,000 we borrowed initially from the bank, and we're at 318,861.20. You paid more in interest than you paid for the original house. Now, there's just some cost of living that we have. We have to live somewhere. We need to be buying something or renting something or something like that. But that's just a really amazing thing to think. Over 30 years, we actually spend more in interest than we do for the house initially. So that's why people do things like, okay, maybe I want to get a 20-year or a 15-year. Maybe I want to refinance and get a lower interest rate or a shorter period of loan. It costs more per month, but you pay it off faster and you don't pay as much in interest. So it's a very big deal for everyone. It's the same kind of thing for college loans, just maybe on a little bit smaller scale. Maybe you're borrowing a little bit less than that, but you're probably paying it off in maybe 10 years, something like that. So a lot of college students are having like $300-400 a month in just college loans. So it's a big thing to think about. All right, but let's end with a positive here. We're going to talk about something called future value. This is where you're saving for the future, investment. So you are putting away money. So you say you start putting away $100 a month every month until you retire. So you're making that kind of save for retirement or save for college. So a lot of parents have like 529 plans to save for their kids' college. That kind of idea. So you're putting money away and the bank is giving you interest for putting the money in their bank. So you're earning interest. Everything in this formula means the same thing. P for payment, I for interest rate per payment, N is the total number of payments. But notice our N has a positive exponent now. Yay! We're multiplying. We get positive values here. And it's the value we're saving for in the future. All right, so let's take a peek at an example. So if there's two things that I can give you as my pearly words of wisdom, save early and buying cash. So this is example for saving early. The more you put away now, when you first are young, it will accumulate so much more interest over time because it's exponential growth. So if you start saving later in life, you will never be able to get back that time to be able to do that. So save early, start putting away right away, and buying cash. Don't get caught with those credit cards and interest rates and all of that. It just takes so much of your hard-earned cash. All right, so we want to figure out how much would the account be worth when we retire. So I want the future value. If I put away $25 a week, so like 5 of your fun little Starbucks foo-foo drinks a week, and we have our 1 plus I, our interest rate per payment, we're going to say we're averaging 8% interest over the course of that loan. So 8%, and we're doing this per week, so that would be 52 times per year, and then raised to the n. So what would our n be? Well, we're going to do this 52 times a year because it's weekly for 40 years. So I'm saying that we're going to start work at, say, like 22, maybe retire at 62. That'd be a little optimistic. It'd probably be longer, but we'll make it sound better for you. So how many total payments would that be? Well, that's 2,080 times you're going to get interested on this in this investment, each payment. And then the -1, and then don't forget the over I, 0.08 divided by 52. All right, so when we do this big picture, we're going to take whatever's in the bracket, that big disaster, and we're going to multiply by 25. So just to kind of walk through the order of operations here. So 1 plus 0.08 divided by 52. And then raise that to the 2,080. That's how many payments we'd be getting interest for. And then -1. and then divided by, and again, don't forget the parentheses on the bottom here. You want to make sure that you're dividing by that entire expression. So let's check in with that number. Now that 15,000 number, that's the value we're going to be multiplying by. So we're saying we're going to do $25 per week. Just think about if you put 100 out front of here, if it's $100 per week or a 200 per week. As you work longer, hopefully you can increase the amount that you put in, but then that's going to give you even more money. But we're just assuming you just stick with the 25 a week. And if you just stick with 25 a week, you're actually going to get to a savings of $381,424.52. Not too shabby considering you're only putting away 25 bucks a week. Now, not all of that is interest earned, right? So the part that your investment part is the $25 a week, and you did that 2,080 times. So how much a part of this was your investment? So you did $25 a week for 2,080 times. It's a lot of times. That's $52,000. So your part of this investment was $52,000. That means the interest that you earned from the bank would be 381, 424, 52 minus that 52,000. Not too shabby when you calculate that. So almost 325,000 or so from the bank that you would be earning just in interest. So it can work for you too. It's not just a negative, but we need to understand how that all plays. So the more you put in, the higher the interest rate, the longer you do it. These are all ways that you can maximize and get more value for your money. But understanding exponential growth and decay is pretty critical to understanding how we can save and buy things in our everyday life.